Welcome back to Linear Algebra for Economists. In this video, I'm going to show you how you could use a Python coding environment to help you with linear algebra calculations. The environment that I suggest that you use is found at cocalc.com, where we can just sign in either with our Google account or even with a Facebook account. After registration and signing in, you will be able to see your projects. Cocalc will have already created you one called My First Project, so let's just click on this. And in your project, you have the option to create or upload files. Let's just call this a file. Here you have to pick what environment you want to use. Let's go with Jupyter Notebook. Pick a kernel of Python 3, and there you go. You have a Python environment in which you can work and write codes and execute those codes and so on. Now, with the magic of video editing, I've already written a bunch of lines of code in which I want to present you with the basics of how to use Python for linear algebra. First of all, we want to import the library NumPy. This is a very large library of many different commands that will be useful for linear algebra. So the first I want to show you is the np.array or numpy.array command, which will take in a list of numbers and return it in the form of a vector. So if I execute this cell by pressing Ctrl plus Enter, it will return the vector 1, 2, 3 as a row vector. Now, if I want to use column vectors, then what I need to do is create a list of lists. So I will put square brackets around 1, creating a list out of it. Square brackets around 2 to get a list out of it as well. And if I execute this, I will get a column vector out of 1, 2, 3. Now I can also add or subtract vectors from each other using this Python environment. So I've created two vectors as shown here, and with the print command I will print out their sum. So you can of course add these component wise. 1 plus 2 is equal to 3, 2 plus -7 is equal to -5, and finally 3 plus 3 is equal to 6. We can also take linear combinations of these vectors. So if I have these a, b vectors, then 3 times a minus 2 times b is going to be this vector. You can crunch the numbers to check that the math checks out. And this way you don't have to do the calculations on paper. This way Python will do it for you. Next, we can also type in matrices into this Python environment. So let's print out this list of lists, which is going to be a matrix 1 through 9. This is a 3 by 3 matrix, of course. I can also ask for random matrices by the command np.random.randint, standing for random integer. And I will ask for elements between -10 and 10, and I will ask for a 3 by 3 matrix in this case, and it will provide me with 1 if I print it out. I can also change the dimensions of it. So if I want a 2 by 3 matrix, it looks like this. If I want a 5 by 7 matrix, that will look something like this, and so on. And I can also change the range of the elements. Now next, let's see that addition and subtraction also works the same with matrices. So I've generated this random matrix M, which is 2 by 2 and has elements -2, 6, 4, -3. Likewise with n, and I've printed out m plus n, which we can get by adding these two matrices coordinate-wise. I can also find their difference if I like, so if I write m minus n here, then I will have the difference of these two matrices. And I can also take linear combinations of matrices, so if I have this A and this B, then 3 times A minus 2 times B is this matrix. Now, do note that I do need to use these little stars for multiplication. So if I just write 3A minus 2B, it's going to return a syntax error. So I need to put these multiplication signs here for it to work. And NumPy also has a command built into it that can handle transposes of matrices. So not very surprisingly, if I have this matrix A, then this is its transpose, so the reflection about the main diagonal. If I have this B matrix, then this is its transpose. And we can also add these together if we like. So these were the codes. If you want to pause the video and then copy it, then this is the point to do it. And not very surprisingly, Python can also handle matrix multiplications. So in here I'm going to generate two 2 by 2 matrices and then see their product. Now, not very surprisingly, Python can also handle, of course, matrix multiplication. So in here I'm going to generate two 2 by 2 matrices and then multiply them together in both possible directions. Now a quick comment on the matrix multiplication syntax in Python. So if I use this star or asterisk multiplication sign, then it's not going to return the matrix product, but it's going to perform element-wise multiplication. So let's see how that works. So if I have the matrix A, which is 3, 2, 4, 5, and have B, 1, 0, 0, 1, which is of course the unit matrix, then the matrix product should return A. But now if I multiply these together, you can see that it's not going to be A, but it multiplied A by B element-wise, deleting these two non-diagonal elements. But if I use this at symbol, then it's going to actually perform the matrix multiplication, and I'll be left with A times B in the sense of a matrix multiplication. Similarly, if I have C and D random matrices, C is a 3 by 4 matrix and D is a 4 by 5 matrix, then of course we know by the rules of matrix multiplication then this should return a product, so C times D does exist. But if I type in C times D with this asterisk, then it's going to return an error because it cannot multiply it element-wise together because they are of different shapes. But if I use the at sign, which does refer to matrix multiplication, then there is no problem. It will return the matrix product of C and D. So if I have this A, which is 7, 9, 1, -8, and B, which is 4, 2, 1, 1, then these are the products A times B and B times A, which we can also check by hand. So let's just do that now. So here we have the two matrices A and B that we want to multiply together. A is denoted by blue and B is denoted by red, so as to make a difference. And to calculate the products, we need these schemes that we have seen before. A times B is going to be 7 times 4, which is 28, plus 9 times 1, which is 9. 28 plus 9 is going to be 37. Then the top right element is going to be 7 times 2, which is 14, plus 9 times 1, which is 9. 14 plus 9 is going to be 23. Bottom left element is going to be 1 times 4, plus -8 times 1. So that's 4 minus 8, which is negative 4. And finally, the bottom right element is 1 times 2 plus negative 8 times 1. So that's 2 minus 8, which is negative 6. And we can see that this is the result that Python also returned for us. Likewise here, the top left element is going to be 4 times 7, which is 28, plus 2 times 1, which is 2. 28 plus 2 is going to be 30. 4 times 9 is 36, minus 8 times 2, which is negative 16. So 36 minus 16 is going to be 20. And then we have 1 times 7 plus 1 times 1, which is 7 plus 1, which is 8. Bottom right corner, we have 9 times 1 plus 1 times negative 8. So that's 9 minus 8, which is 1. And we can also see that this is the result that Python returned us. Now let's see how this might be useful for us. So from the matrix multiplication video, you might remember this example where Alice had to do the shopping for 3 different weeks for 4 different products, and she had 5 different supermarkets with varying quantities that she needs to buy and varying prices in each of the supermarkets. So we can use Python to multiply these 2 matrices together for us. We don't really need to crunch the numbers ourselves on paper. So if I copy all of these quantities and all of these prices into 2 matrices like this, then I can have Python multiply them together for me and then return the results. So this would be the product of the 2 matrices. And by the way, when I was making these slides, this is how I did it. I didn't calculate all of this by hand, of course. And then this is the result that we also got there. So now let's see how we can query some data out of this matrix, because of course in real life this might be like a 100 times 100 matrix, so it might not be that easy to see what's going on in the matrix. So first let's try the command minimum of the results. So print np.min of the results, and this is going to return us 148.75, which is of course the minimum of all of these elements. Now let's suppose that I'm not interested in the minimum of all the elements, but let's say I'm interested in where Alice should go shopping in the first week. So that would require that I find the minimum of the first row. The way to do that is with this command. So this 0 stands for the first row. Python has indexing convention of starting with 0. So the 0th row stands for the first row. And if I execute this code like this, I will get the minimum value of the first row, which in this case turns out to be 210.64. So this is the shop that Alice should go to in the first week. Likewise, in the second week, she should go to the first shop. And finally, on the third week, she should go to this 4th shop here. Now I can also ask Python to return immediately which shop she should go to. If I execute the code print np.argmin of the results, then I will see that actually is the 5th element that is minimal out of all of these elements. Now this is not very helpful because we only have shops indexed from 0 to 4. Remember, we have 5 shops. So this 5 would mean the 6th shop, which is not really a feasible solution of our problem. But this refers to the fact that this element, which is the minimal out of all of these elements, is the 5th element. So if I want to see what the index of the minimum element of the first row is, then I would have to go with this code. And this code returns us 4, which of course means the last column, meaning the 5th shop. And I can do this, of course, with the second week as well, in which case I would need to send Alice to the first shop. And I can do this with the third week as well, wherein I need to send Alice to the fourth shop. And this is also the result that I marked in the worked example back then. Now let's see how we can use Python and the NumPy library to help us find the determinant of a matrix and also solve systems of linear equations. So in here I've generated a random 3x3 matrix like before, and I've also generated a column vector x of shape 3x1, and I calculated b to be m times x. So of course this would correspond to a system of linear equations with this coefficient matrix and this right-hand side vector b. Just to spell out more clearly, this would be equivalent to the system of linear equations 8x minus 2y minus 6z equals negative 44, negative 6y minus 5z equals 21, and so on and so forth. To find the determinant of m, which is a prerequisite that it's not zero if we are to have a unique solution, we can use the command np.linalg.det, standing for linear algebra and determinant of m. And apparently the determinant of this matrix is 32 plus some rounding error. And the solution of this system of linear equations, so the x that I took originally, was negative 8, negative 1, and negative 3. Now let's see how we can find x knowing m and b. So I can type in m and b as before, and I can call upon the command np.linalg.solve m and b, and then have it print out what x is. And it is going to return the same exact x. So this linalg.solve command takes in a matrix and a vector, and it will automatically solve the system of linear equations described by that matrix and that vector. Now, a last thing I want to show you, which is also going to be the topic of the next video, is how one can use NumPy to find the inverses of matrices, which we'll, like I said, learn about in the next video. So this is done with the command np.linalg.inv, standing for inverse. And the cool thing about inverses is that if the matrix has a non-zero determinant, then of course the inverse will exist. And if I multiply the inverse with the right-hand side vector, I will also get the solution of the system of linear equations. We will see why this is happening and how this relates to simple linear equations. So hopefully you found this video useful, and in the next video we are going to be moving on with matrix inverses. See you then.